Welcome back. The twin prime conjecture. Twin primes are primes which differ by 2. For example, 3 and 5. They are twin primes. 5 and 7, they are twin primes. 11 and 13, twin primes. 17 and 19, 29 and 31, these are all twin primes. The conjecture is that there are infinitely many such pairs, P and P plus 2, both primes. That is, the conjecture is there are infinitely many twin prime pairs. This conjecture is still open, that is, it's not completely proved, but much progress has been made. Here is a beautiful theorem. Consider prime factorizations of positive integers a and b. Let a equals p1 to the power n1, p2 to the power n2, so on, pr to the power nr, where these pi's are primes, n's are the powers of the primes in factorization of a. Likewise, find a factorization of b, p1, p2, so on. So notice I'm saying there are same number of primes. Well, that's easy to do. If any prime is missing, I just give it power 0. So I'm allowed powers to be greater equals 0. N sub I is greater equals 0. Likewise, M sub I greater equals 0. Right? And what are P1 through P1, PR? P1 through PR are primes. Then what can we say? Once you have prime factorization, how do you obtain GCD? Well, you know many methods, but here is a theoretical method, and that is take the minimum of the primes, a minimum of the powers. All right, minimum of the powers. That is the GCD. Whereas the least common multiple, you take maximum of the powers. That's the least common multiple. Moreover, A times B equals GCD times LCM, the least common multiple. Okay, this is a reasonably challenging proof, but anyhow, let's go look at an example. If A is 12, B is 18. 12, factorization, prime factorization is 2 to the power 2 times 3 to the power 1. 4 times 3 is 12. 18, 2 to the power 1 times 3 to the power 2. 2 times 9 is 18. What is the GCD? According to the theorem, you have to take the minimum of the two powers. So take 2 as a base, minimum of 2 and 1 is 1. 3 as a base, minimum of 1 and 2 is 1. GCD of 12 and 18 is 6, is it? Yes, it is. That's the greatest common divisor. Likewise, least common multiple. You take the same base, 2 and 2, take maximum of the power. Maximum is 2. Take the same base, 3 and 3, take maximum of the powers. Here is 1, here is 2. 2. 4 times 9, 36. Is 36 the least common multiple? Yes, it is. Moreover, what is A times B? It's 12 times 18. It is 216. And so is GCD times LCM. That's also 216. Okay. So this is an important theorem. You take factorization of your integers A and B. Keep the same base, prime base. When you take minimum powers, you get GCD. When you take the maximum powers, you get LCM. Product of GCD and LCM is equal product of your A and B. Okay. Here is another very nice theorem, Bezout's theorem. If A and B are positive integers, then there exist integers st, so that GCD can be written as SA plus TB. This is called combination, integral combination. GCD of A and B can be written as a number times integer times A plus integer times B. For example, we just saw GCD of 12 and 18 to be 6. Well, note 6 can be written as negative 1 times 12 plus 1 times 18. All right. Here is another example. GCD of 30 and 50 is 10. 10 can be written as 2 times 30 plus minus 1 times 50. 60 minus 50. All right. The numbers S and T such that GCD AB is SA plus TB, they are called Bézout coefficients. The equation GCD AB equals SA plus TB is called Bézout's identity. Here is a beautiful theorem. If you have ABC as positive integers such that GCD of AB is 1, that is A and B are co-prime. They are prime to each other. Co-prime, okay? GCD of AB is 1. If A divides B times any other number, then A has to divide the other number. Well, why is that the case? Well, GCD of AB is 1. What did we say by Bézout's theorem? You should be able to write that GCD as a combination of A and B. SA plus TB equals 1. Multiply this equation by C. SAC plus TBC equals C. Now, what do we know? A divides BC. If A divides BC, it divides TBC. A divides A, so A divides SAC. So A divides SAC, A divides TBC. So it has to divide their sum. In other words, A has to divide C, which is what we want to prove. So that's it. Which brings us to another important result. If P is a prime number and P divides product of integers, right? If it divides a product of integers, then it has to divide at least one of the integers, okay? Why not? What if it did not? See, look at P and A1. Well, either P divides A1 or P and A1 are co-prime. That is, GCD of P and A1 is 1 because P is prime. Either P has to divide this guy or they don't have any common divisor other than 1. Well, if that is the case, then P has to divide the rest of them by our result here. When A and B have GCD 1, then A has to divide C. So P has to divide the rest and keep arguing until P divides something, one of these integers. Here is the last theorem. Let M be a positive integer, ABC be integers. If AC is equivalent to BC modulo M, if GCD of C and M is 1, then A is equivalent to B modulo M. What does equivalence means? AC equivalent to BC mod M means M has to divide AC minus BC, the difference. AC minus BC is nothing but A minus B times C. Now, GCD of M and C is 1. Well, in other words, M has to divide A minus B. That was Bézout's theorem we just saw. Okay. If M divides A minus B, then A is equivalent to B mod M. That was proof of this result. So this completes lesson 14. Okay. Next videos we'll start in lesson 15.